everyone, welcome to the lecture 24 of the course Climate Change and Extreme Events. In the previous lecture we have primarily talked about um, how to set up, let's say, statistical or machine learning based models, what are their pros and cons, and then we have also talked about what sort of the data limitations, data requirements, and then for example, if we have to assess the validation and calibration of our statistical and machine learning based models. Then we have also talked about in which scenario, in which case studies, the statistical model will perform better, and then in which case or which scenarios the machine learning model works better. In the previous lecture we have talked about how do we set up these models, data driven models. For example, how do we do that validation and calibration approaches, what sort of k-fold approaches or different types of validation approaches we can apply, so that we can have in kind of accuracy assessment of our predictions, so that we have to sure about, let's say, if our model, statistical model or machine learning based models are giving some results, what is the accuracy of those results from that analysis. In today's lecture we will talk about, let's say we have already set up the model, we have selected the model, then we have set up the model, and then we have also thoroughly checked the model using different types of matrices for accuracy assessment, plus different types of accuracy validation algorithm, k-fold algorithm and all, LOCCV kind of algorithms. Once this is set up, the model has been already set up, how we can use these model for projecting for future extremes or some sort of doing scenario analysis. Why it is important? Because eventually when we are developing some sort of model, we are aiming towards that we have to know about what could be the potential future if the continuous trend is likely to happen in historical period, then what would be the behavior of climate extremes in the future scenarios and different scenarios. For example, let's say high global heat or global warming case, or high emission of the GHG gases, or let's say medium emission of the GHG gases, or medium warming level or low warming level scenarios like that. Therefore, it is very important to know about those outcomes from the already set up model. So, in this lecture we primarily talked about how we can use that setup model to generating different types of scenarios or analysis of future extremes in future conditions. So, in this lecture we will primarily talk about the role of scenario analysis in climate projections. We will explore different approaches to projecting future climate extremes. We will learn about uncertainties and model assumption in climate forecasting, and then we will talk about several, some of the real world applications of scenario based analysis using already set up models, so that we can analyze what is the differences in climate extremes behavior in different scenarios. So, what is scenario analysis? Scenario analysis is a systematic way to explore potential future climate conditions based on different assumptions. What are those assumptions? Particularly it could be low greenhouse gas level, high greenhouse gas level, or let's say medium level of greenhouse gases, or let's say what would be the socio-economic impacts of different activities happening different parts of the earth, and what would be their consequences on global warming or GHG emissions like that. So, that is called a potential future, because we are not very sure about what is likely to happen in future. So, therefore, we predict the future in different scenario basis, and then we basically look at the climate extremes at different scenarios like that. Why it is important? Because when we have scenario analysis, it helps policymakers or researchers prepare for various climate related risk, and we know about what would be the climate risk in different scenarios, and then we can compare it, and then we can suggest, okay, this kind of the scenario and whatever the hydroclimatic or let's say greenhouse gases emission level we have to maintain, or let us say the temperature rise threshold we have to maintain, so that it will not we have a very high amount of or magnitude of climate extremes. What are the common applications? For example, we can talk about flood risk management, flood risk assessment, heat wave intensity predictions, and drought projections. So, these are the some of the common applications areas where we can look at the scenario analysis and we can predict what is likely to happen in the future conditions. What are the key climate projection scenarios? So, in CMIP 5 or coupled model, climate model scenario 5, we basically can divide our different scenarios into different 3 parts. For example, it can be represented by representative concentration pathways, RCPs. So, there are 3 types of scenarios were proposed in CMIP 5 simulations, previous climate projections simulations. So, that is RCP 2.6, where we have assumed that the emission is going to happen in future or near future or mid future or far future conditions. The emission would be low emission, and aggressive mitigations like that we will apply, and therefore, there will be controlled on all these emission scenarios. In RCP 4.5, we have assumed that it would be a kind of an intermediate scenario, where we will reach the stabilization of greenhouse gases by 2100. Then RCP 8.5 is kind of a high emission scenario, where we are talking about continued fossil fuel use and how we can that is going to increase the greenhouse gases emissions in that particular scenarios like that. In the recent development CMIP 6 program, we have already divided the socioeconomic pathways into 3 different improved forms, which is called shared socioeconomic pathways. So, that is SSP 1 or SSP 3. So, I have listed here 3. There are many other shared socioeconomic pathways which are possible in CMIP 6. So, SSP 1 is basically sustainability pathways. SSP 3 is called when we are talking about some sort of regional rivalry and fragmentation among different countries and all, and that leads to more emission of the greenhouse gases. SSP is a kind of still we are relying upon fossil fuel based development, and therefore, there will be lot of greenhouse gas emission in the atmosphere, and therefore, that will increase the global warming even further. When we have this kind of the scenario assessment, we would be able to finalize or we have to understand what would be the impact of these different scenarios on climate extremes. So, you can understand here also, for example, in the shared socioeconomic pathways, we have divided into different socioeconomic development phases. For example, the one is called the sustainable growth model. The 2 is basically middle of the road, or we have a little bit away from the sustainable model. 3 is basically the moderate regional rivalry or sort of kind of conditions where you have relatively higher amount of greenhouse gas emissions and global warming. SSP 4 is a kind of inequality where we are talking about not continuous or homogeneous development of socioeconomic conditions across whole world. And then SSP 5 is basically we are talking about fossil fuel development, where we are still using the fossil fuel kind of and also emitting a lot of greenhouse gases. We are not using any further renewable sources, solar energies like that. So, if you talk about all these different scenarios, you have different level of global forcing or warming forcing conditions, watt per meter square, and based on that basically it defines what is the level of the global warming in that different scenarios. But when we are talking about CMIP 5 previous scenarios, we are only looking at different warming level excluding these socioeconomic pathways. So, we have for let us say SSP 2.6. For all other scenarios you have only RCP 2.6, RCP 4.5, 6 and 8.5 without any development phases or improvement phases or socioeconomic pathways like that. So, this is called scenarios. Why it is important? Because we do not know exactly what we are not very sure about what is likely to happen in future. So, if we are not sure about future, then we have to define our future into different scenario base. When we have scenario assessment, then we can do our modeling into different scenarios, and then we can tell about to the policymakers or to the scientists or ground application that if we are following this particular road or this particular pathways, our climate extremes or different hydroclimatic condition would be follow like that. If we are following, let's say, SSP 5 or some higher emission scenarios or higher socioeconomic scenarios, our climatic extremes trajectory is completely different from sustainable growth model like that. So, therefore, we can compare it, we can compare the magnitude wise, frequency wise as well, and then we can suggest what kind of the growth model we have to adopt in a certain region with the help of policy implementation or some sort of mitigation planning for mitigation plans in that particular regions like that. What are the methods for projecting future extremes? So, we talked about statistical model, we talked about machine learning approaches, and there are something dynamical models also. So, statistical theory, let us say we can talk about time series extrapolation, we can talk about ARIMA model, we can talk about frequency analysis, we can talk about extreme value theory applications in time series model. Then we can talk about machine learning. There are neural network or random forest or these kind of machine learning approaches. We can merge it together and we can understand what is the climate pattern or extreme weather classification in the future steps or the historical part of the data set. Then there is a dynamical model where we are using the general circulation model GCMs, which are physics based, physical representation of different processes within that particular framework, and they basically simulate that processes and then gives the output out of from those models like that. Then we have also regional climate models for localized impact, and that can basically also impact tell about what is the overall behavior of different hydroclimatic extremes properties at a different particular location. So, this is the one of the table which can gives you an sort of ideas what kind of the methods we can use for projecting future extremes in the future scenarios. So, for example, extreme value theory, which is a frequency analysis method which can be applied to analyze the robust or rare event probabilities. That is sometimes requires a long historical records. If we do not have that, might create some sort of uncertainties in the results. Then we have ARIMA type model, autoregressive moving average model, which are simple, effective for stationary data. Suppose your data is non-stationary, there is a trend in the data, there is a significant jump in the data. In that scenario, your ARIMA model probably will not work, and therefore, it can give you poor performances and there is some sort of uncertainty in error in your predictions. Then there is a GCMs and RCMs that dynamical model requires comprehensive physical modeling with high spatial resolutions as well, and therefore, it can create some sort of computational expensive results. When we are talking about GCMs, the results might be low resolution, spatial resolution. When you are talking about RCMs, they are limited to a smaller or fixed region. Maybe we can, if we have to apply it for the larger region, we have to scale up, either we have to reduce the resolution of that data, or maybe we can increase the computational efficiency of our modeling framework so that we can apply it for and we can project these future extremes. Then there is a more deep learning based or machine learning based models which are called neural networks or random forest or tree based models, which are good in non-linear pattern recognition and feature importance ranking. that sometimes requires data intensive and that lot of data set, and primarily these are the black box nature, and therefore either we have to input some sort of physics or process understanding in the model, so that they can understand the physical processes which are there can be within the model and can give you more insight about the processes in the climatic streams. So, and when we are talking about random forest or machine learning model, there is another problems which we have already discussed in the last class, that there might be the possibility of data or model can be underfitted or overfitted, and therefore we have to make a balance between underfit and overfit problem, and then make it single optimized fit by applying some sort of penalties or regularization techniques L1 and L2, and therefore we can solve the problem of overfittings like that. Now, when we talk about, let's say we have already applied we know that scenario, what are the scenarios, we know that what kind of the modeling framework we can use. When we are talking about climatic streams or projecting future extremes in future steps, there are uncertainties which can be generated. What are those uncertainties? Primarily it can be divided into three parts. One is called model uncertainty, which are differences between climate models. Suppose you are running multiple models at the same times. Some models have different sets of processes interpretations, some has primarily data driven techniques, or some are based on time series modeling. So, it is possible that there might be differences in the model uncertainties, because all of them are representing the processes data set differently. Therefore, it is possible that your output can be different. Then there is a scenario uncertainty, where we are talking about we do not know exactly, let us say after 50 years, 60 years, 70 years, what is likely to happen. Suppose what we are thinking right now in this today, it might be completely different after 50 years. So, therefore, scenario uncertainty is also very important, and there is another uncertainty which is internal variability. It is possible that there is a natural climate fluctuations, some sort of internal processes which can also be responsible and can give provide the uncertainty and can so that is the way where these uncertainties can be originated and can be part of your model projections or results. How do we mitigate these uncertainties? We can take the ensemble mean of the model, multi-model comparison, and then we can assess the ensemble average value of model, so that we can have what is the uncertainty in the different modeling approaches, or maybe we can assess the probabilistic approaches. We have discussed about the uncertainty quantification in the previous classes, the probabilistic approaches to understand the risk assessment of these different future projections. So, this is one of the graph which shows that after 2020 we have different scenario assessment, and each different scenarios you have complete band, and when it is increasing, which means towards close to 2100, the band has been increased quite significantly. It is covering the larger region, which means uncertainty is quite high when we are looking at far future using the current historical data set. There is another figure here which tells about when you are looking at the near future events or projections, primarily the internal variability and scientific uncertainties are predominant. But when you are talking about moving away from the near future conditions, the scenarios uncertainties are the one which are primarily dominating the system, or plus some sort of scientific uncertainties. So, that is basically where major uncertainties are originating in the from the model itself. So, these are some of the examples of some of temperature or climatic streams and their projections, and then how we can infer from different scenario based assessment. So, this is the projected extreme heat waves for multiple different for near future and far future scenarios, as well as different RCPs, 4.5, 4.5 scenarios, 8.5 and 8.5, like basically higher emission scenarios like that. So if you look at the near future conditions, RCP 4.5 scenarios, the probability of occurrence of your extreme heat events in entire Europe is relatively lower compared to, let's say, near future higher emission scenarios, where the extreme heat waves probabilities or occurrences has been slightly increased in the higher emission scenarios like that. But we are talking about, let's say, the occurrences of the extreme heat waves in 4.5 or scenarios for far future. It seems that in the far future, the lower emission scenarios, we have also seen a very significant rise in the heat extreme heat waves in the entire Europe like that. And similarly, when you are talking about higher emission scenario for let's say far future time period, we have also seen a very significant rise in the heat waves across Europe. So which means that when we are talking about lower scenarios, the things are relatively controlled in few years or near future terms. But when you are talking about far future scenarios, it might possible that the things will go worse, or maybe because of some uncertainty or some basically increase in the increase in the particularly the forcings, we have higher occurrences of the heat waves in the future steps like that. And when we are talking about high emission scenario, of course, the mid or the near future scenarios tells not very relatively higher increase of the heat waves, but when you are talking about far future, the things are very changed, and the impact of these extremes are quite higher compared to the present conditions like that. So what are the key findings of these particular results is increasing frequency and intensity of heat waves, that is projected rise in global average temperature from 1.5 degree and 4 degree, that is basically it is here it is calculated. What are their impacts? Urban heat stress and energy demand spikes, and multiple other linked extreme events, kind of the climate extremes will also be going to be increased. There is another example of projecting precipitation extremes in Indian region across the Indian subcontinent, and here what we can see that the rainfall patterns. For example, this is precipitation, this is maximum temperature, this is minimum temperature, and this is basically we are talking about different scenario based assessment 126, 245, 370 and 585. Basically here we are talking about how the precipitation is going to be evolved in the future time step, future conditions. So the precipitation in the lower emission scenario is not going to increase that much, but when you are talking about higher emission scenarios, the precipitation will rise like more than 100% or more than 50% in several part of the western part of the India. When you are talking about the maximum temperature, the relatively increase in the lower emission scenarios were not that much high, but when you are talking about extreme emission scenarios, it shows that the temperature has been significantly increased in the future time steps, or this is the average value for the future data set, which tells about most of the regions are likely to be faced by rising 4 degree or above 5 degree rise in the temperature in the future type step, that is maximum temperature. Then we have also the minimum temperature rise, that basically tells about in the lower scenario we have lower rise, let us say 1 or 1.2 or 1.8 degree centigrade. But when we are talking about higher emission scenario, we will have higher increase of the temperature in the minimum temperature, which is also generally calls night time temperatures like that. So there is the clear sign of telling about the climate variables is likely to be changed under different shared socioeconomic pathways or global warming conditions. and that is basically is reflected by different climate variables. So, what would be the implications of these results? More intense short duration storms, that is going to happen. There is a shifts in monsoon timing and variability, and there is a high chances of increased probability of extreme flooding in coastal areas, and that is also more frequent and prolonged drought in arid regions like that when we are talking about this. Then there is another case studies of projecting cyclones and storms, which tells about the typhoon peak intensity is likely to be increased in future time step. Presently we are in category 2 and category 3 hovering around, but in future time step, let us say beyond 2050, it will be in category 4, which means the typhoon intensity is likely to be increased due to warmer sea surface temperature, and that is basically shifts in the cyclone tracks affecting new regions, and it is basically also be responsible for storm surges risk, sea level rise, and that is exacerbating the coastal flooding from these storms like that. Then there is another case studies of Mumbai, where because of the future conditions RCP 8.5 particularly, the annual coastal flooding is likely to be increased by 2050, and therefore there are multiple places here. It is marked by red, which is completely showing that those places is likely to be inundated by 2050 because of the high chances of sea level rise, and at the same time we have flooding and urban flooding events in those areas like that. So, therefore, this kind of the analysis is very required in terms of understanding those regions where you have higher probabilities of occurrences of these inundation areas in the different urban clusters like that. Then is another case study which is basically for Murray and Darling Basin, where it suggests that the eastern North Australia and the rangeland and southern Australian region, the drought risk, the percentage time, the frequency and duration has been also changed. When you are talking about different drought index, that is SPI and SPEI. So, that is called standardized precipitation index SPI, and SPEI is called standardized precipitation evaporation index. So, SPI generally defines the meteorological drought conditions, and SPEI generally defines the hydrological drought conditions. So, when we compare all these results based on these SPI and SPEI, it tells about in all your future scenarios or higher emission scenarios, it is likely to be increased, and therefore there is a high chances that we have more frequent drought events in those regions like that. This is the case study of the Murray and Darling basins like that. Now, what is the how we can use these case studies or scenario assessment for policy decisions? So, probably when we are talking about importance of projections in decision making, we are talking about essentially long term planning for infrastructure and disaster response, because we are not talking about the the long short term duration, but we are planning for, let us say, what is likely to be happening in entire 2100, what is the frequencies and climate extremes events like that. Then we are talking about adaptation strategies, which are basically climate resilient city planning. We are talking about improved water resource management. We are talking about what are those climate change drivers which can be which can be controlled, so that we can have a little less impact of greenhouse gases impact or emissions in the atmosphere, and then so on other processes, or the climate change effects, which is basically can be your hydrosphere, lithosphere, and all other different parts of environmental side. Then we are talking about climate change adaptations. We can talk about water harvesting or building sea walls or crop diversification, agroforestry adaptation or restoring the degraded ecosystem or improving efficiency of irrigation system. Or let us say we are talking about climate change mitigations, where we are talking about clean and renewable energies, longer term goals like that, sustainable energies, sustainable agricultures, enhanced waste management, and carbon pricing like that. So these are the steps when we deal with, when we have the scenario assessment, we can go for these types of steps, so that we can minimize the effect of different climatic extremes in different warming conditions like that. What are the challenges in scenario analysis? We need to have a higher resolution climate models, that is data limitations. We need to have a computational challenges in running high resolution simulations. We also want to have translating the complex projections for policymakers and the public, so that it should have communication properly from the scientist perspective to the policymakers and to the public, general public. And then for different scenarios, we have different types of challenges for mitigations. For example, when you are talking about lower emission scenario, low consumption, low population growth, reduce inequality and all. When you are talking about SSP 4, SSP 3, that is we are talking about policy focus on security, barriers to the international trade, high inequality, slow economic growth like that. When you are talking about SSP 4, that is policy focus on elite, highly consumption, highly inequality, low to moderate, medium economic growth, and low population growth in rich countries, high in other countries like that. And when we are talking about higher emission scenarios, that is we are talking about policy focused on the free markets and high consumption, effective traditional cooperation, reduced inequality, high economic growth, and we are talking about low population growth. So these are the challenges associated with the different scenarios, which also takes into account when we are modeling the climatic extremes in different scenario assessment. Future direction in the climate scenario analysis, advanced modeling, higher resolution simulation using AI enhanced model can enhance the accuracy of our climate projections or future projections climatic extremes. The uncertainty quantification should be improved, so that we can accommodate or calculate accurately the uncertainty of different component, and also the overall uncertainty of the probabilistic forecasting of climate extremes events like that. Then there is an integration with the socioeconomic models. So when we are talking about climate models or data driven models or something, so they are talking about essentially the climate extremes, what is likely to happen, the magnitude, frequencies, inter-arrival period or return periods like that. But how we can convert these information to the economic impact assessment, that is very important. So therefore, there is an integration of socioeconomic models with our climate projections or climate extreme projections, so that we can accurately assess if this kind of the extreme events is likely to happen, what would be the economical impact in a certain regions like that. So therefore, to increase the future directions or the climate scenario analysis, we have to advance the modeling, we have to enhance the predictive capabilities. When we have advanced the modeling, we have more predictive capabilities, so that we can predict the climate extremes more accurately. Then we can improve the uncertainty quantification, we have more understanding about which processes or which variable has more uncertainty and how we can reduce it. Or let us say there are 3 different uncertainties areas, how we can know about each of them and how we can accurately or is there a way to basically minimize those uncertainties as well. Socioeconomic impact assessment, basically, which is very important. We are only talking about climate extremes, magnitude, frequency, inter-arrival period like that, but how we can convert this information to socioeconomic impact, that is equally important, so that we can have a complete picture of future projections in the of different extremes in the different regions like that. And then we have integration with the socioeconomic models that we have already discussed like that. So what is the key takeaways of this particular lecture is, scenario assessment is very helpful because it basically gives you idea about what is likely to be happen in future in terms of climate extremes under different scenario conditions, under different assumptions. For example, if you are talking about low emission scenarios, middle the emission scenarios or higher emission scenarios, and the equally we are talking about what would be the socioeconomic growth or model, so that we can talk about what is likely to happen in the climate risk in the different future projections. And when we are talking about future projections, we have also talked about through the different case studies that the climate extremes are likely to increase, and therefore we are particularly focusing on how do we maintain it, how do we minimize that negative impact caused by these climate extremes by looking at previous studies on a certain region and then translating that information to the policy makers so that they can understand it and they can plan it appropriately or make some sort of policy so that it can reduce further the negative impact of the climate in that particular region, or how we can basically accurately calculate the uncertainties, for example, in our projections, and we can mitigate their effect further or reduce that uncertainty so that we can have better and reliable results out of that climate models like that. So, this is primary what we have discussed so far in this particular lecture. In the next lecture, we will primarily talk about what is the total summary of week 8, and we will also talk about the assignment of week 8, and then after that we will discuss about the solution of week 8 assignment. Thank you so much for your attention.